In this short video, I'm going to show you how to go ahead and execute something like Euler's method in GeoGebra. I'm currently running the GeoGebra app, so if off of the Chrome browser, for some reason, I'm not able to run my other portable file as described. Same process, except you're going to go over to your View tab if you're running the actual portable version. In other words, if you're running it from Google Chrome, then you come over here, and this is kind of where your file and edit stuff is. So we click on View, and we want to set up a spreadsheet. And in this spreadsheet, we can now begin to type things in. Now, you can also close these windows if you want, and you can do that similarly. In the full applet, you can actually just click X and close them, but here I actually have to go to View and uncheck certain things. I'm going to leave them open for now, but you can go ahead and uncheck them. Nothing gets lost. If you go back and click the graphics view again, it pops back up. So what I want to do is I want to, first of all, typically I already know, sometimes I know the solution that I'm trying to use Euler's method to try to model. So I'm just going to pretend like I already have a solution, which is maybe 5e to the 0.2t. And so there's the solution. So that would be the solution to dy dt equals 0.2y. And so to do this, I'm going to come over here. I'm just going to label my columns, make this as pretty as you'd like, but I keep it fairly simple. And so these are my three columns. So in here, I'm going to go ahead and lay in my my initial time and my initial condition for that time, which is that at time 0, I have an output of 5. Okay, so dy dt is going to get calculated on the basis of either t, y, or both t and y. In this case, I'm going to say that my differential equation is 0.2y. Okay, so to execute that, in order to calculate it based on that, what I want to come over to, and you don't need to enter this over here, this is just for reference, mainly to show what we're using. Well, I want to take 0.2, so I'm going to type in equals 0.2, multiply that by the value of y. Well, the value of y that I want to calculate dy dt based on is in b2, so I'm going to type in b2, and if you press enter, you'll notice that it calculates dy dt as 1. Now, of course, this is dy dt means that's the change in y per a 1 unit change in t. Now, we haven't specified what delta t is yet. One easy way to do this, well, you could manually either type these in or set your increment and then copy and paste down. What I actually like to do is I like to come over here and I like to set delta t. And this is just going to be my place where I'll enter my current delta t. So maybe right now I want it to be 0.25. So I press enter. And now, instead of having to go up here and add 0.25 to 0, what I'll actually do is say equals cell A2. So this is the only row that we need to set up. After this, it's all easy from here on out. And I want to add to that the step size, right? So I want to take 0 and add the step size to it. So to make sure that I don't have to keep referencing the cell, what I'm going to do is a dollar sign, an F, 4, dollar sign, and then 4. And what that does is it says lock column F, lock row 4, so that even when I drag this formula down, it doesn't start to reference cells deeper and deeper down. And I'll show you what I mean by that. So right now, you can see this cell references A2 plus F4. If I drag it to the next step, well, it did the correct computation because it's now taking A3. Since A2 wasn't locked, as I move down, this cell changes right here, but this cell stays the same. I always want it to reference F4. This just makes it, like I said, really easy so that if I change the step size, then all of these numbers adjust as well. So check this out. If I come over here and now type in 0.5 and press enter, all of those change. And I can still drag and keep that formula going if I don't have enough, my domain isn't big enough. So now what I want to do is I want to take the y value up here, and I don't want to lock that because I always want it to take the y value right above, and I want to add to that the right proportion of that rate of change. Well, it's the step size. If the step size is a half, and dy dt is 1, then I want to add 5 plus 1 times a half. So in other words, I'm taking the step size, which again, I'm going to say, okay, reference F4. I always want it to reference F4 for the step size because I'm not going to be changing that. Multiply that by the dy dt. you actually have to type that in. So C2. Oh, no, it entered itself in. Press enter, and now you should see that it's taken 5 and it added half of 1 to it. Now, if I change this step size, the cool thing is that, again, if I change this to maybe like 1, then, well, now it reads that take 5, add 1 copy of 1, makes it 6. If I change this to 0.25, it should only add a quarter copy of the dy dt. Okay, so enough said there. Well, this formula is good to go because this is referencing the cell 0.2 of the cell to the left of it, so that's good. This row is now set up, and so now I can take these guys, highlight them, and copy them all down at once like this. And there we go. So now I have all the dy dt's, and they are getting bigger, which makes sense because the y values are getting bigger, and dy dt is a function of y only. So now I have these values, and again, I can come over here and change the step size to whatever I want, and I'll get varying outputs. Now what I want to plot is just my t and y pairs, so I'll highlight those, right-click, go over to Create, and you want to create Polyline. So what that does is now it creates a basically a polynomial line, a polynomial fitted line. And so now I can even go in here and see what effects this has, which is pretty cool. I can change this to 0.5 and see, well, first of all, my t doesn't go as high because I have many step sizes in between, but you can see how much better of an approximation that is. Or 0.1, enter. And now I'd have to really zoom in here because my step size is so small, but you can see how nice of a fit that is. Even here you can kind of see some of the deviation. So that's how you do it. Fairly basic, simple way to do it. If you do extend these rows, however, these points are not going to extend out further. You're going to have to come back over here and either delete the polyline, or you could do, well, I guess you could do object properties. I don't want to do that. Let's just go ahead and remove the polyline. Okay, we don't want to delete the function f. We want to make sure the polyline's highlighted. So polyline, delete that. And we need to delete all the points as well. But anyway, now you'd have to go back through and highlight this again and create a new polyline if you were going to have more t's. So maybe plan ahead when you do that. Either highlight more values down the line so that if you were going to extend the domain of t further out, based on having such a small step size, it works really easily. So anyway, hopefully that's been helpful. That's how you do it in GeoGebra. Excel has a similar process. I just like this better because I can plot the solution, the actual solution, and I can really see things quickly and clearly by referencing things in here.